So this is going to be a relatively short video introducing thermochemical equations, which we are then going to use in a process that calculates delta H indirectly using thermochemical equations. So a thermochemical equation, wait, we're going to get through this first. Whoops. Is an equation that's either representing a phase change in this case, or a chemical reaction, and every thermochemical equation has the delta H associated with it. So in this example, enthalpy is increasing from the solid water being converted, or this phase change, to liquid water. In order for that to happen, energy has to be absorbed by the system, that's solid water, from the surroundings. Could be an ice cube on a counter, and the air is warmer than the ice cube, so it absorbs that warmth from the air and starts melting. Remember, if we are absorbing, Q is positive, and delta H is also positive. And those delta H's again are given in kilojoules per mole. So for every mole of ice that melts at its melting point, which is 0 degrees Celsius in 1 atmosphere, 6.01 kilojoules are absorbed by that solid ice. So once again, that system absorbs heat, therefore it's endothermic, and delta H is positive. So endothermic equations, whether thermochemical equations, whether they're representing a phase change or a chemical reaction, have the delta H associated with them. Another example, this is going to be an exothermic reaction. It's combustion. Again, we have that methane reacting with molecular oxygen to form CO2 and water. The system, the reaction of methane and O2, gives off heat. So it's exothermic, therefore delta H is negative, or delta H is less than 0. So I'm Madison. Shadow's barking in the background. Hopefully he won't continue. 890.4 kilojoules are released for every 1 mole of methane that is combusted at 1 atmosphere. And the thermochemical equation, methane plus molecular oxygen giving CO2 and water, plus its delta H in kilojoules. So the stoichiometric coefficients always refer to the number of moles of a substance. In this case, this phase change, these are 1 to 1. But if you reverse a reaction, because we can go not only from solid to liquid, but liquid to solid, the sign of delta H will change. So if we go from liquid to solid, the magnitude of delta H remains the same, but it's opposite in sign. So melting, solid to liquid, is an endothermic process, delta H is positive. Liquid to solid is an exothermic process. The liquid has to lose heat in order to freeze, so it's negative. Same value, but opposite sign. If you should multiply both sides of the equation by a particular factor, then delta H has to be treated the same way. So if we are melting 2 moles of water, solid water, to 2 moles of liquid water, the delta H needs to be multiplied by 2 because this delta H is determined for 1 mole. So to melt 2 moles of ice, we need 12 kilojoules of heat energy absorbed. So the physical states of all the reactants and products must be specified in thermochemical equations because their state affects their delta H's. And we'll see that when we work some other problems. So solid to liquid water, we know delta H is 6.01 kilojoules. But if we're going from liquid state to the gaseous state, the delta H is 44. It requires more energy or more thermal energy to convert that liquid to vapor. So here's basically a dimensional analysis problem based on the stoichiometry of a thermochemical equation using delta H as a conversion factor. This is white phosphorus combusts in the presence of oxygen to form P4O10. O10. This is the compound that produces the bright white light in fireworks. And if we have 266 grams of that white phosphorus and burn it in air, we're going to produce P4O10. And this is the delta H associated with that reaction. 1 mole. So we can use that delta H to help us do this calculation by using it as a conversion factor. And what we're going to do is take our grams of P4, convert those to moles of P4 using molar mass, and then we can use the delta H to convert to kilojoules of heat energy in a dimensional analysis equation. So this is our mass of P4 times the molar mass, canceling the grams, converting to moles, and then this relationship. Now notice that it doesn't show the negative. And that's because this question is worded in this manner. Heat is evolved. So that means we assume heat is given off and do not need to use the negative. Oops. So grams cancel, moles cancel, and we get 6,470 kilojoules. So the right way to answer this question is 6,470 kilojoules, although I should note that we need 3 sig figs. So I'm just going to go ahead and write that in scientific notation. 6.47 times 10 to the third kilojoules are evolved. When 266 grams of P4 are combusted. If we were asked to give the delta H for that mass of P4, then the delta H would be negative, to show that that was an exothermic reaction. So terminology matters. And finally, this is a table for some heats of typical reactions measured at constant pressure. So we have delta H's in kilojoules per mole. That's what you'll find in tables. We have heat of neutralization. So that's a reaction between an acid and a base. It's exothermic for these two, for HCl and sodium hydroxide. Heat of ionization, an endothermic process. 56 is 0.2 is positive. Heat of fusion, that's freezing. We've seen this before. 6.01. So that's heat of fusion, solid to liquid. It goes both ways. We're either melting or freezing. If it's freezing, it's negative 6.01. Heat of vaporization, another phase change, liquid to gas. It's also positive. Endothermic, we have to absorb energy. And heats of reaction can be positive or negative, depending on what that reaction is. And next, we are going to calculate delta H's in two ways, directly and indirectly. But we'll have to introduce some new terms before we do those calculations.